the main thrust of our work now will be that of the alpha carbon, i.e. the nucleophilicity of that said alpha carbon of these carbonyls. So really what we can investigate, what we will investigate, is this area here, because this proton is quite labile. So it can be deprotonated under acidic conditions to give an enol, or under basic conditions to give an enolates. In both cases, we have a nucleophilic carbon, yeah, which can then attack an electrophile. So think of the electrophiles that you've previously encountered, and herein this will be attacked by enols and enolates. The enol itself you've come across before. Remind yourself, for example, when you added water to an alkyne, say for example if we did a Markovnikov addition of water using an acid catalyst, then the net result would be, of course, your enol. Your enol will tautomerize to give you an, in this case, a ketone. So an enol is really a tautomer of a carbonyl. Make sense? So let's focus. Realize that because in previous work, when we looked at this carbonyl, we're looking at attack of on the carbon, this electrophilic carbon. But now we will look at exactly what's going on in the alpha proton, because strong bases can remove that alpha proton under acidic conditions. If we have weak bases, we can remove that proton under acidic conditions. Why? Because there's an inductive effect, yeah? And herein, the main reason why. So not only do the inductive effect make it more labile, but as we can see here, we have here that proton having a pKa of 25 compared to a normal alkane of pKa of 34, 36, yeah? Herein, when you deprotonate, you get that enolate, and realize that enolate have a resonance structure. So that enolate is stabilized by resonance. The more stable the conjugate base, then of course the more acidic the species. So this is why we can state that that alpha proton is quite acidic. The first resonance structure shows the nucleophilic nature at that carbon, even though the second resonance structure has the negative charge on the oxygen, which really is the major resonance contributor because the charge is best suitable on the more electronegative species. So herein you have the mechanism for the enol tautomerization. So you can protonate, this in the case of a weak base. So we protonate, and then of course you can see the deprotonation will take place to give you the enol. Herein, on the basic conditions, yeah, we can deprotonate to give us the enolate, and you can see that enolate has that resonance structure. Realize previously we can, if we look closely at the enol, we can probe the nucleophilicity of that enol by looking at this resonance structure. So now you can see the nucleophilicity at that carbon. Remember that we have a resonance effect and we also have an inductive effect. If you look closely at a normal hydrocarbon, like alkane, pK of 50-60, yeah, but here you can see with acetone, pK of 16. You compare that with an alcohol, of course, pK of 16, sorry, pK of 19, 16. If you have a halogen, i.e. an electron withdrawing species present on that alpha carbon, then you can see there's a rapid decrease in the pKa, i.e. the species becomes more acidic, i.e. we have a more stable conjugate base. Can you tell me exactly why this has a pK of 16 compared to this? So this guy here, yeah, with the phenol ring is more acidic than the base standard acetone. Why? We know that this fella here, this is the diketones, has very acidic protons. Look at it, pKa of 9. Why is this? These beta dicarbonyls have very low pKa. Why? The reason why, of course, is because we can generate 3 resonance structures from these, and they become critically important later on down the road. 3 resonance structures, so we have a very stable conjugate base. So we could ask something like this, for example, which is the wrong resonance of 2,4-dione. Yeah, have a look at it carefully, pause, and then we can talk about this in the discussion sessions. Herein, you can see that enol acting as a nucleophile. You can see the negative charge, yeah, on here from this resonance structure attacking the electrophile, and so you end up with a species where we can deprotonate our proton to give us a substituted product. We can also use this flavor of the enol, yeah, to attack the electrophile directly. Herein we have the enolates. We've already shown you the deprotonation step, and so here we have this flavor showing the negative charge on the carbon attacking the electrophile to give us our product. We could also use this flavor as well. Doesn't have to be an aldehyde, a ketone, or beta dicarbonyl. You can see that esters are quite useful. Nitriles are quite useful. But you can see there is a difference in the pKa. During our discussion sessions, we'll talk about why there is that difference. They are less acidic. Why? Herein, I've asked this question: which is the correct order of decreasing acidity? I know for a fact that, yeah, I can get rid of this one. Why? Because I know that the alkane is the least acidic, i.e. the compound with the largest pKa. So that leaves me with the other four choices. Have a pause here, work on that, and we'll discuss it during our sessions. So the main mechanisms that we'll be covering right now in this part of the work is halogenation of that alpha carbon and alkylation of that alpha carbon. The bases that we use are either non-catalytic, such as sodium hydride and LDA, which will explain what this is later, or catalytic, which are usually alkoxides or hydroxides. We also look at the enamines, as in the Stork-enamine reaction. So let's probe the non-catalytic bases, sodium hydride, LDA, react only once, while catalytic bases react repeatedly. Why? Because non-catalytic bases are stoichiometric, i.e. if I deprotonate with a hydride, I end up with dihydrogen that is irreversible. On the other hand, if I deprotonate with a hydroxide, I end up with water. I can easily deprotonate water to regenerate my hydroxide. One of these are predominantly kinetic and the other one is thermodynamic. Have a think, pause, and see if you can come up with that answer. The non-catalytic base, leads to monoalkylation because it's stoichiometric. And LDA is one of the more popular ones. We make this by reacting the amine with lithium metal. And so what we have is an amide. It's a very powerful base. Lithium diisopropyl amide. We, of course, being a powerful base, we have a non-nucleophilic polar solvent. In this case, an ether. Aprotic, non-electrophilic, I should say, polar solvent, i.e. an ether. In this case, we have THF at low temperatures. On the other hand, sodium hydroxide and the alkoxides, are catalytic bases, i.e. multiple alkylation can occur. So I want you to look carefully at this diagram. And we're working with an enolate. And what I want you to envisage is this enolate is just a complex nucleophile. So if you envisage it like that, then there is going to be no change in that structure. All that's going to happen is that you're going to bond an electrophile to your carbon. So quickly, here's an electrophilic center. Let's put a delta plus there. We know this is alkyl halide. We did this when we were in organic 1. You can see here, for example, here is an electrophilic center. It's a carboxylic acid derivative. And so the main reaction is addition-elimination. So this nucleophile will substitute X. Here we have another electrophilic center. It is a carbonyl, like an aldehyde or something. So you know for a fact that the nucleophile will attack it, followed by a quench. So the main product, the major product is, of course, an addition. So what have we done? We've added, that enolate with a hydrogen across the carbonyl double bond. Yeah, because there is your tetrahedral center with your pseudo alcohol. If we have an unsymmetrical carbonyl, in this case we have 2-methyl-cyclohexanone, there are two possible pathways. We can go via this proton, you can see it's a secondary carbon, or we can go via this proton, which is tertiary. The first pathway, of course, is the most easily accessible pathway. So this is the enolate that would be formed faster. The second pathway is, of course, the more substituted enolate. So this is, of course, the enolate that is more stable. Of course, from our chemistry that we know in the past, this most easily accessible species is, of course, our kinetic species. And the more substituted enolate is, of course, the more stable species, is your thermodynamic event. In a kinetic event, this predominates under mild conditions. What is mild? We need polar aprotic solvent, non-nucleophilic base, like LDA, right? And low temperatures, minus 78 degrees Celsius is ideal, right? Because this prevents the kinetic species from equilibrating with the thermodynamic species. So LDA with the EFA at low temperatures, kinetic. On the other hand, in the thermodynamic events, we need strong base, of course, but in a polar protic solvent, preferably a solvent that relates to our base. So here we got sodium ethoxide, and we're using ethanol as our base, and you can see the temperatures are quite high. So therefore, the thermodynamic enolate is going to dominate, under these conditions. Pause right here and have a think about what the answer should be. We will continue this discussion when we meet next. So herein we'll view the halogenation. Remind yourself that we're deprotonating the alpha proton. This event can occur under both acidic, i.e. enolic, or basic enolate, by the enolate event. We'll go through both of these mechanisms with you. Herein, you can see that the protonation, in the case of a weak base, i.e. acid catalyzed system, protonation is followed by the generation of our enol. Our enol can then attack the halide to realize this trivalent oxygen, which can then be deprotonated to give you your desired product, i.e. substitution at the alpha carbon. Could you draw the product for me, please? Here, we have the basic events. And so the base will come in, deprotonate to form our enolate. Remember, your enolate has a resonance structure associated with it. And then, of course, attack, in this case, we're using dibromine. So attack on dibromine, realizing our substituted product. And we now can review this reaction, which is the iodoform reaction. Remind yourself that with the hydroxide and the halogen, yeah, we have an autocatalytic reaction. The iodoform reaction is a reaction that we use to test for an acetyl group, i.e. a methyl ketone. Methyl ketone. We talked about the importance of the acetyl group in biochemistries, acetyl-CoA, etc., acetylcholine. And so in the past, what we did was use this test to see if we do have that acetyl, i.e. methyl ketone residue in our substrate. The reaction is quite simple. You deprotonate and then of course you halogenate. Yeah, in this case we're using iodine. You deprotonate again and halogenate, etc., 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 until we get to total halogenation substitution of the free hydrogens. This realizes a rather good leaving group, so it behaves as an acid derivative. And the last hydroxide can come in, yes, and throw out the Ci3 minus, which can be quenched to give you, which gives you iodoform. So iodoform will indicate that there is an acetyl residue present, plus you can, from melting points and other characterization, identify the carboxylic acid and therefore identify what species you're working with in the substrate. Here we have a, say, on nomenclature. I want you to pause right here and try to do this one. Please pause. And then we'll discuss it during our meetings. So next I want you to probe this reaction mechanism. Consider what we did before, previously. It says propose a mechanism for the acid catalyzed conversion of cyclohexanone to 2-chlorocyclohexanone. Unfortunately, I've given you both, yes, the starting materials and the products, and so you can work out from there, because first thing you want to do is, of course, you want the acid catalyst, yes, to protonate, to activate that carbonyl, and so your lability of your alpha proton will increase, and you can make the enol from that, which will then attack the chlorine, and then of course you can imagine deprotonation yielding your product. So pause right here and fill in the blanks. I hope you paused. Now let's look at another problem set. This shows you a scheme where we're asking you, yeah, to identify where the error is in the mechanism. Have a probe of this one, pause, and then we can review this next time we meet. Another question. This is the base catalyzed halogenation of ketones. And so here we're proposing a mechanism for the reaction of 3-pentanone with sodium hydroxide to give you 2-bromopentanone. So herein, what you need to do is to draw 3-pentanone and draw 2-bromo-3-pentanone and see exactly what mechanism what the mechanism would look like. It is a base catalyzed system, so of course we're talking about forming your enolates. Here you can see immediately, right, the acid addition of the acid catalyzed substitution of bromine on the alpha carbon. And then, of course, we can use a base to eliminate said hydrogen bromide. In this case, we got pyridine, right? I prefer pyridine. So you eliminate the hydrogen bromide to form that degree of unsaturation. And of course, that is your enol. Remind yourself why the enol is so powerful. There's an electrophilic center here, and there's an electrophilic center here at the beta carbon. With that, we move on. So why don't you go ahead and answer this one for me? And once you envisage the answer, we can discuss that in class the next time we meet. An interesting reaction that we need to consider is that of the alpha halogenation of carboxylic acid. It's very useful synthetically, and we use a strange set of reagents. We use bromine with phosphorus tribromide. Why do I find this interesting, or why is it so interesting? This Zelinsky. Well, you can see here I can make an amino acid using ammonia. Terribly important. Here I can make alpha hydroxy acids. And of course, I can eliminate also to give me unsaturated acids. So here's an alpha beta unsaturated acid. With that, we can start playing with some nomenclature. Note the number of carbons and note the reagents. With that, we come to the end of the first part of our enolate chemistry, and we'll continue with the second part in another clip.